works. My name is Primož. I come from Slovenia and I love Pascal. So that's all you need to know about me. And this works, that's excellent. So you can find me mostly everywhere as Gabor42, that's first 4 letters of my surname, except on Stack Overflow when I don't have numbers, and on Twitter where I go by the Delphi Geek, because the other one is my private Twitter account. And my blog is thedelphigeek.com, where you can find lots of stuff that I wrote over the years. Since we don't know each other here, it's a very different crowd from the one that I'm used to talk to. A few words about me. I'm about as old as Marcos, so our path was quite similar. We both started with Pascal on Sinclair Spectrum, except mine was Highsoft Pascal. But my first programmable device was HP Calculator 41C, which my father used for his architectural work. It had a card reader and you could write assembly code. And actually, before I wrote my first program, I hacked my first program on this machine. Yeah, it came with a moon lander which said type how much fuel you want to inject, and it would land softly, and I always crashed. So I analyzed the program and drew the flow chart and find out how much fuel exactly I have to inject to land in one try. In this time, I also started working on PDP-11 machine in Fortran, assembler. Then in university, I started working for a local Slovenian computing magazine, the leading computing magazine. At that time, there were 2. We had CP/M machines at the university when I first learned about Turbo Pascal, because we had Turbo Pascal 3 there, running on CP/M, not on DOS. I was working on VAX machines in VAX Pascal, which was a powerful language in those times, because VAXes had virtual memory, and you could just go and declare, okay, C is array of 1 to 1 million. Who cares if I don't have enough memory for that? It will work anyway. The memory got paged to disk and read back. It worked. And I used Perl and all sorts of stuff in those times. We started with DOS, of course, Turbo Pascal, and then later Borland Pascal, and then later Integrated Debugger. That was the biggest win of the times. 5.5, I think it was. With brief discourse into OS2, and then with Delphi, I basically moved to Windows and stayed there. I wrote for a few articles, for a few magazines besides Monitor, for Delphi magazine, for Blaise Pascal magazine. I wrote on my blog, and I wrote a few books. Talk about that in a second. But most of this time, last 25 years or so, I work at FAB. We develop software for TV broadcasters. So here in Spain, if you are watching subtitles on TV España or in TV Barcelona, I don't remember how exactly it's called, this is our software for preparation and for transmission of those subtitles. And we do teletext systems, we do TV stuff that works over IP, we do asynchronous communications that run with 2 gigabytes per second with specialized hardware, and all that is done in Delphi with really small amount of assembly code, which gets smaller and smaller every year as computers get faster. And in all those times, I was using lots and lots of stuff: Perl, PHP, Java, JavaScript, for basic, assembler, Prolog, Logo, probably more, Python definitely. But I always return to Pascal and I always stayed at Pascal. People have asked me yesterday, why Pascal? And we actually had reason in 90s why to start working with this company on Pascal and not on C, because those were the two choices at the moment. And our reasoning was C allows us to do everything, but we know we'll make mistakes. So let's pick a programming environment which will check array indices for us, which will check integer overflows, which will prevent us from use types incorrectly. So we chose Pascal, plus we all hated brackets. Brackets on brackets on brackets on brackets. We all met with Lisp in our high schools, and that's just terrible. So Pascal. C got later lint and type checkers, so it's a bit better, but it's so much easier to shoot yourself in the foot with C or C++ than with Pascal. So yeah, I write the blog, and if you go to the delphigig.com, on the right side you'll see this link, presentations, and all my sessions from previous years, all source code, all slides is available there. This session will be up there sometime today in the afternoon, so if you download, tomorrow you can download it from there. And as Sergio had said, I write books. The first one was Delphi High Performance for Packt Publishing. It goes through different views on how to write performance software with Delphi, since this is something I do daily. From choosing correct algorithms to knowing Delphi internals, to know when something got copied around or when it's just referenced, to how the memory manager works, because that gets important, especially in multi-threaded environment, to how to use parallelism and so on. And about the same time, I released Parallel Programming with Omni Thread Library. That's my self-published book. Omni Thread Library is my parallel programming library for Delphi and Windows at the moment, just Delphi in Windows, which I developed, I don't know, 5 years up to releasing this book slowly. This was my 4th, 5th parallel programming library. First 3 or 4 attempts were all crap, but then I got the right idea, I think, because people love it. And it got so big, I usually didn't know what is inside, what I did, what I didn't do, how to do something, and then I decided just to document it, and I wrote a book. So this is reference for me. When I have to find something in my library, I open my book. That's the idea behind it. And then later, a few years later, I published Design Patterns with Delphi. That's also an interesting story. Packt people have contacted me and said, hey, would you write a book on patterns? And I said, oh, I hate patterns. Because patterns, in my mind, were Java and UML. And I hate both of those. But I took a week and sat down and researched and said, okay, there actually is no good literature about Delphi and patterns, what is applicable, what is not applicable, what's completely stupid to do in the Delphi environment, and so on. And so I did write a book, and I must say I love this book. I was almost forced to do it, but I really, really love it. It is not your typical pattern book. It goes through the patterns. It says, okay, those are useful to know in Delphi. First, I start with why it is useful to know patterns, but I won't go there today. But then I go into, and that's how we do it the Delphi way. Ignore all that Java, C approach to patterns. That's how we do it, because that makes sense in Delphi. And I still think it's a very good book. All this stuff, all the code from these books is on GitHub also. So if you just Google for GitHub and title, you will get the code. And just those days, last week, a second edition of Delphi High Performance was released. 2 new chapters, everything adapted from Delphi 10.3 to 11.3, which is quite some versions actually, and to current time. So if you want, you can get it now. They're all available in printed or electronic version, and the electronic is PDF plus EPUB plus mobile, so you can pick. If you want to talk about anything, I'm here all week, so just catch me somewhere in the hallway. I like to talk about stuff. Today, I focus on multi-threading. This will also be a focus of my workshop. So in those 4 classes, we will go through all of this, but slower and with more code. So today, focus is on slides. Workshop focus is on the editor. But I will backtrack now to 90s, 80s. Before Terminate and Stay resident programs, we had single tasking. So we could run multiple programs, yes, on a machine, but just one after another. And that was tedious, it was clumsy, it was cumbersome. And I'm talking here about single-user machines and multi-user machines, but there were no multi-user machines because you had to put, I don't know, your cards into the queue, and they were processed at some time, and then you get to pick your result. Okay, but luckily, then we got multitasking because someone decided, well, maybe we could do a small time slice of one program and then small time slice of another program. But before that, we got something very, very terrible. Cooperative multitasking, which was in Windows 3.1, 386, and then in Windows 95. It was multitasking where one program said, okay, I did as much as I want to do, you can transfer control to a different program. And all changing from one program to another program was voluntary. Program had to say, okay, I'm done, you can pause me now, you can run another program, and that was terrible. If you remember Windows 3.1, one program could lock up and everything would lock up because the program would not release control to another task, not even back to the operating system or to the user interface. So, to something that we use now. Preemptive multitasking is an idea which said we can run multiple programs, but we won't run them to the completion. We'll run small part. Nowadays, that's about 20 milliseconds, give or take, of one program, and then we'll pause it, and then we'll run a different program. And then we'll pause it, and then we'll run the third program. And the program can still say, I have nothing to do. You just call a yield function of the operating system on Windows. There's something else on Linux. As I said, I'm a Windows person, sorry. But typically, you don't do that. You just leave the operating system to do those switches. And tasks now run in some order. It's not a specified order. You don't know how they will run. A task may get 2 slices, one after another. If maybe this one is waiting on user input, this one is waiting on something to come over the socket. So operating system says, okay, those 2 are basically waiting. Let's run task B again. And once we had that, it was a small step to multi-threading. And let's ignore for now what a thread is. Let's say thread is something inside your program at this moment. We could do this on single CPU, of course. We started doing this on single CPU, and that's exactly the same as with normal task, single thread multitasking. But now the operating system says, okay, we run thread 1 from task A, and so on and so on. Again, in some order which we don't know, we can affect a bit by setting different priorities to those threads, but it's usually better not to do that. But then we got multiple CPUs, and that's the situation we are now. And that's the situation where stuff gets really complex. Because now operating system really runs 2 programs at the same time. It has 2 cores, or nowadays, I don't know, 64 cores. It can run 2 programs or 64 programs. But it will still switch from one to another and from thread to a different thread. Some stuff can happen, some stuff cannot happen no way. So a thread may jump from a CPU to another CPU, unless you prevent operating system from doing that, and again, it's better not to do that. Operating system can run 2 threads from the same process at the same time on multiple CPUs, no problem. What it will never do is to run the same thread on multiple CPUs, and we'll see immediately why. So now, let me now explain what a process is and what a thread is, because I ignored this in my introduction. A process, you will find this definition in many different, you will find it defined in many different ways. But for the purposes of this talk, let's say a process is basically a database that holds information about your program. So what parts of memory belong to the program? What file handles are open? Which file sockets are open? Which user interface elements, Windows buttons, and so on, so-called GDI handles on Windows belong to our program. Thread, on the other side, is the execution state of the program. So where the program is at this moment, what is the state of the registers, what is the state of the instruction pointer, what are the contents and location of the stack. So only when we put those 2 together, our program can execute. So actually, every program always has 1 thread. We call it main thread nowadays, usually. And it's if you do your normal Delphi application, it's your single thread where programs runs. For example, if you press F5 and to create a breakpoint and debugger pauses there, your thread gets paused. Control goes to the debugger. When you press F9 to run, debugger transfers control back to your program, which checks, and the operating system checks this state and knows where to continue execution. So now that makes it a bit more reasonable why 1 thread cannot run on 2 CPUs at the same time, because it would have 2 execution states, and that's not possible, simply. A thread is a single CPU, which may jump from CPU to CPU, path through your program. Why both? Processes are protected one from another. So if one process allocates memory, another process cannot access this memory, cannot change it, trash it. That happened on Windows 3.1 a lot, and then everything went down, you pushed reset button. So on serious operating systems, that's not possible. But also processes are heavy. They require more memory from the view of the operating system because it has to manage those collections. They are slower to start, and so on. Threads on the other side are light. They're quite simple to start, although it's still, I don't know, 10 milliseconds to start the thread, for example. But they are not protected. So one thread can access memory that was allocated in another thread which again makes sense because this memory belongs to a process, not a thread. And that's also actually, although that's a problem, this is also great, because otherwise you would be only able to release a memory in the same thread where you allocated it, and that would cause all sorts of problems. So why do we do that? Why complicate with multiple threads? And usually there are two answers. Either we want a responsive UI, so we all know that. First reason for multi-threading was always, I'm doing this data processing in my program and user interface blocks. And our first solution was call application.process messages multiple times, but then user could click a menu. Okay. Another solution, move your data processing into a background thread, so your main thread is responsive. It's also very important on mobile devices. For example, on Android, you definitely must not block your user interface thread, or weird things happen. And the other reason is for the program to run faster, of course. We always wanted that. In the old times, it was simple, because 20 years ago, we said, you want a faster program? No problem, wait a year. Computers will be much faster in a year. But then that stopped, basically. So now computers get more cores, but they are not that much faster. And there are two sub-cases to this faster program execution. One is simple and one is very hard. So the first one is handling multiple clients. So you have a server you wanted to handle. Server runs on a machine with 64 cores. You wanted to handle 64 clients at the same time, not one by one. You need multiple threads, each handling one client. The second, faster data processing, that's usually hard. So if you want to process data in a faster way, well, there are occasions when this is, as we say, embarrassingly simple to do it parallelly. Just put data in some parallel process and it will go n times faster, but usually it's hard, and we'll see later why. So now that we know why, let's talk about how to do it. On the OS level, we have support for threading. We could do nothing without that. On Windows, we have create thread. On POSIX machines, we have pthread, underline create, and pthread family of functions. On some platforms, languages, we have compiler support for that. For example, in JavaScript, definitely in C#, we have async await keywords, which are actually very pretty, but hide a terrible computer magic behind how this is implemented and so on. But for our situation, we don't have compiler support, we have runtime library support. So in Delphi, and I believe Lazarus is quite simple, quite similar here, we have begin thread function, which basically wraps this create thread. And we have tthread class, which presents a bit nicer interface for working with threads. Still, it's sometimes good to know that this exists, because you cannot set thread stack size with tthread, but you can do it with begin thread. But okay, so now we come to the scary part. So why are we not doing multi-threading all the time? Yeah, as I said before, when we want to make something faster, we run into problems. And typical first source of the problems is that all those threads now want to access the same data, because our programs are designed alongside some global data, object, presentation, arrays, list, doesn't matter. That's typical how we do stuff, and now we want to read from those global data, but the problem is when we want to write back to this global data. So a few of the problems here. Simultaneous writing. We have some integer, And as I said, memory is shared between threads, so two threads can do data is data plus one. What will happen? Yeah, something. If they execute one after another, data will get increased by one and by one. But actually, when you write something like this, compiler does something like this. And even if you write ints of f data, which gets translated into quite optimal assembler instruction, CPU internally does something like this. You cannot prevent it. And now, let's say we have 10 here, and two threads that execute at the same time on two cores. Temp becomes 10, temp becomes 10, temp becomes 11, temp becomes 11, data becomes 11, data becomes 11. We lost one. And that's basically the best thing that can happen. Usually sharing data problems end in access violation, not in wrong values. So, okay, we cannot write into same location from two threads. Okay. But can we write and read? No. A bit different example, we are sharing a list. And we are processing data in that list. Marco have said var inline variables are great, because what he didn't mention is that I don't have to care what kind of data is stored in this shared list. I just write for var t. I don't have to care about type of this t. Okay, but I have a reader here, and I have a writer. What will happen? Yeah, this goes from 0 to count -1. Someone deletes an element. This count is checked, is retrieved only once before the for is executed. So we'll try to access one element more than there is, which will typically work and will not crash because list is over allocated. So when you delete one element, it's the same memory block, just uses less data. But consider this. We are inside the for list, and another thread adds data to the list. That's actually less safe than the previous example, because the list may run out of space, and to add a new element, it has to allocate new memory block and release this one. So this will switch the memory block behind the t-list. This will still work on the old memory block. Yeah, and quite possibly at the same time, or just after this, some other thread says, hey, I need memory, and gets the old memory block of this list, and this thread happily writes over the old memory block, which now belongs to the third thread, which tries to do something with this memory block, and yeah, it all blows up. Third problem, shared data, shared classes, shared interfaces. This will, of course, not work. One will win, one will lose, one will overwrite. The resulting value, we have lost memory, at least, if not more. This will also not work. So if I check if list is assigned, but do the same on the second thread, both will then happily create this object. Same problem. I will go into solutions for this problem at the workshop, so don't worry. And then you have the hidden behavior. So when you know all of this, this will bite you. This happened to me last year. So after all those years of multi-threading, caring about problems, this has happened to me. It cost us a week of problems before we found what's going on. We had something like this in the code. So we are now reading and reading, yes? What can go wrong? Because the code then got data.memory, or what is called pointer to the memory block, and then use pointer arithmetic to go through that block. So it was really safe, except this. Because in Delphi, get size is implemented as seek to beginning, seek to end, to seek to beginning to retrieve the current position, seek to the end to get the size, and return to the current position. And those variables are local, so still okay. Because memory stream, when you seek to beginning, it changes shared field, F position. So when you are reading size, you are changing position. And at this time, the other thread kicks in and overrides this position, and bang, everything crashes. But just sometimes. Most of the times it works. So what to do about that? We have synchronization primitives, which are, as we'll also look into, sometimes implemented in the runtime library or provided by the operating system, or you can do it manually if you know what you're doing. But basically we say I want to enter this critical section, and now I will change my data, and then I will release my section so others can use it. And the implementation here will prevent two threads to proceed on this path. So one will succeed, one will stop here and wait. And only when the release is called, the other will proceed. Excellent. We have solution, except we don't. Because first problem, this is not enforced. So if we have this, one thread is carefully written, one thread makes a mistake. All our hardware gone. Data is corrupted. Because this one doesn't know that it has to stop here. They can lead to deadlocks. So if we have two critical sections, first thread acquires the first one, the second thread acquires the second one, and then they try the reverse, and everything stops. And that of course, is usually not like this. Both those successes are hidden somewhere deep in the code in some property getter or something. You don't know where this happens, you just know that it stops. Plus, synchronization slows down execution a lot. We'll also go to this in the workshop. So if you do acquire, modify, release cycle, keep this locked area as short as possible, because at this point you are basically making your program a single-threaded. Everyone has to stop here before proceeding. And the other solution are interlocked operations. This is something that's provided by the CPU itself. So we can do something like this. F data and call atomic increment of F data, and this will work because this gets translated into a special CPU instruction which knows that it has to lock cache before all the CPUs and update the data here and then mark it dirty, so all other CPUs will then retrieve the correct value from the cache. At the CPU level, it is immensely complicated, and I don't really know how it works. But I just know how to use it. Because if you want to read Intel documentation about this stuff, you be ready to read some 1,000 pages of very, very complicated text with very, very complicated diagrams. And we have this atomic increment available on different levels. For example, in Delphi, we have atomic increment in the system unit, which is always included. We have interlocked increment, which comes from Windows, and it's the same thing. And we have T-interlocked class, which implements methods to increment, decrement, exchange two values with locking and so on. I usually like to use this one because I start typing T-interlocked dot code completion, and then I can find the correct function. I'm just lazy. Again, they are not enforced. You can do this. This will get translated into lock increment. This will get translated into increment. And this CPU will know basically nothing about cache being dirty and modified, because again, this at the CPU level, this is again slower than this, but the difference is not as big as with the locking. So interlocked operations are faster, but they are much more limited. You cannot do everything with them, and they are hard to use. They have their place in parallel programming libraries and at some special places probably, but they're not for everyone. If you don't use them, don't worry. That's completely fine. The big problem with multi-threading is testing. Multi-threaded programs are not testable. For a single threaded program, you can write unit tests. You know how your execution path will go through the program, at least to some constraints. But with parallel programming, there are basically infinite possible interactions between more threads. So this, when you see something like this in two threads, you definitely don't know what will happen. One may execute before the other. One may execute after the other. They may execute at the same time. Or maybe this one will start executing, and immediately after this instruction, and we are in the middle of the +1 at the Pascal level, the operating system will say, okay, thread freeze. Another thread will execute now. So this happens even on a single CPU machine. You could run first thread, do first two statements, for example, and then the operating system freezes your thread and starts executing this thread. And the same problem occurs, one CPU. You're not safe. Okay, before I move on, this is still the introduction, sorry. It's the longest part of this talk. We have other solutions. We could write multiple processes which cooperate one with another. For example, modern browsers are all written in this way. You have 30 chrome.exe processes running on your machine at any time. They present themselves as a common user interface, but they are actually different processes because they have protected memory. If JavaScript interpreter crashes in one of the windows, just that process is killed and so on. It's safer. We also have frameworks to do programming on multiple processes and cooperation. We can do parallel processing on a GPU, which typically needs an OpenCL library, and you have to write some code in C or C++, but you can then use it from Delphi. And there are examples on the internet. We can move to bigger environments, to clusters, to grids, to clouds, to whatever. But today we're talking about threads. So in Delphi, it all started with Delphi 2. Version which worked only on 16-bit Windows, and Delphi 2 was the first 32 version working on 32 Windows, and actually the first that was usable. Marco may say that Delphi 1 was a great revolution. It was a great revolution, but it was not useful. You could not really write a big program with it. But it was something new, something we never saw before, so yeah. But Delphi 2, we wrote software in Delphi 2. We sold software in Delphi 2. It was great. In Delphi 2, we had already the begin thread and T thread that I mentioned before. And usual approach to multi-threaded programming was start a thread, tthread.create, and then write a main thread loop inside tthread. Well, you derived a new class, from tthread. You created that class, and you implemented this class .execute, and you wrote your monolithic big threaded code here. And this threaded code looked a bit like example that Marco had, how we wrote Windows programs the Petzold style. You had a big loop, you were waiting for events, you were signaling, you were doing stuff, so on. And then at the end, you terminated the thread, or you could set the thread to auto-terminate. We'll also see about that later in the other session. And the thread would go away. And we had some synchronization tools which more or less came from the Windows directly. So Windows implements critical sections and mutexes and semaphores and events, and doesn't matter now what they are, but we could use them. And writing threads this way is completely possible. We did it. It's a lot of work. It's a big opportunity to make lots of mistakes like we saw before, because this framework just helps you to create a thread, nothing else. Okay, later the thread got better. It got more functions. You could return values from a thread via return value. At some point, I don't know if this was in Delphi 2, it got exception support. So exceptions threads were caught and propagated back to the main thread, and so on and so on. So the code was, of course, improved over the years. But still, there was no good way to write, no known good way, let's say, to write a thread in Delphi. I know because we did it in many, many different ways, and lots of them were terrible. I still have to maintain code which uses tthread in absolutely disgusting way, but I'm afraid to change it because I have no idea what I will break. So I'm just maintaining it. So lots of approaches, incredible amount of bugs. There was very limited support for synchronization, just those Windows stuff. There was basically no support for communication from one thread to another, or from main thread to a worker thread, and so on. Well, stuff begins to get better when we come to tasks. And to my knowledge, well, where I first met this idea was with the .NET 4 task parallel library, which, if I'm not mistaken, many good concepts and ideas from TPL were taken into Delphi's PPL. So Alan Bauer also closely watched this scene, where we got tasks, we got concrete collections. Those are collections which multiple threads can use at the same time without problems. We got cancellation, and then I think in a later version we got parallel 4 about the same time, or maybe even a bit before, we got link for queries and so on. And later we got C# async await. So, but that's the first time I met the idea of tasks. It took me some time to understand what the task is, but it turns out the task is just a change in how you think about things. It's more change in your mind than in the code. So with thread, you give explicit instructions. You say, system, please create a thread. I will use the thread. And usually, unless you do some extra work, you get a new thread each time. Creating a thread takes some time and so on. With tasks, you say to the system, please execute this in parallel. I don't care about how you create a thread, how you manage your threads, what you do with those threads when they are not doing any work. So most of the time when they don't do any work, they go back into some collection that we call a thread pool. So when we need a new thread, we just pick a thread from a thread pool. It's waiting there for us. That's fast. It doesn't take almost no time. The difference is like if you are building new house, do you want to walk around your electrician guide and say, okay, you put the cable here, you put the cable here, you put the cable here, or do you say, I want switches and plugs in this room? That's the difference. And there also we got some new synchronization mechanisms through the years. One of the big changes in Delphi was tmonitor, which allows us to basically use every object as a critical section without having to declare a new critical section, which is incredibly practical. Plus, it is spin lock, and I will talk about that on workshop, not here. But mostly this means that it's slightly faster than critical sections in most cases. We got tthread.synchronize, which allowed us to execute code back in the main thread, so that took care of some of the communication problems. We got improved operating systems support in all those 20 plus years, almost 30. We got readers writer blocks, we got condition variables, and more probably. Those two are most important to me. And that allowed us to write our code much better with tasks, with improved communication. We also, well, okay, improved communication, let's see. We always had a way to send operating system messages from a thread to main window, or from main window to some hidden window which we had to create manually inside our worker thread. That was always there. But we also got tthread.queue and force_queue, which allow us to say, please execute this code in my main thread at some time. Possibly very soon now, but I don't care if this is executed just now. So this is a communication mechanism. We say, please, main thread, execute this code whenever you feel fine doing that. Oh, what did I do? Okay, and then we have, of course, polling, which again we always had, but we got better library support for that. And by polling, I mean one thread manages a list of events, for example, and when it wants to signal something, it writes new events to the list. And the other thread occasionally says, okay, is there something new? No, that's polling. Okay, is there something new? Oh, new event. And it reads it, and what should I do now? And then, of course, you need locking around that, otherwise everything will break again. And we got my iOmni blocking collection, which is implementation of .NET concurrent collections. It's a queue of unlimited size, which allows multiple writers and multiple readers, and all locking is done with interlocked operations, not with system locks. It's quite fast, and as we'll see in the next 5 minutes, it can be quite powerful. And you can also, if you're using Delphi, you can use it with normal tthreads or tasks, or even inside main thread if you need a queue. It's useful everywhere. You don't need my library, the rest of my library to use it. So all those actually are implemented in the same way. They have some shared list and they have some locking. This shared list is the operating system level or the runtime library level or at your level. And this one is shared lists, multiple lists to simplify allocation and deallocation and to speed it up, and interlocked operations. And I said locking is slow, yes, I have said before, but in this case locking is acceptable because you lock for a short time, you just put a message in, take a message out, and you unlock. Plus this locking is managed by some library, it's well tested, it's not, it does not occur in your code. So you cannot forget to put it in your program. It's always there. And if you find out that any one of those is too slow because of locking, it means you are just sending too many messages. Reduce the number of messages, pack them together, or whatever. No one needs to process 20 million messages a second. Collect your data into smaller chunks and send them across. Oh, I have a very, very complicated graph here, but actually it's quite simple. We have two threads as before. As again, this line marks my thread division. Each is using some local data without a problem, but they are also fighting for shared data. and maybe they are fighting for to write a shared result somewhere. Maybe they are processing one list into another list, so they have to lock output list also before writing into it. And with communication, this looks even more terrible, but we can change all this stuff and split data into multiple pieces before we start threads. And then our threads run basically as a single-threaded pieces of code. They have no interaction with outside memory or for writing. And then at the end, you just take output and put it together. That's the communication approach, data splitting, data communication. And with a good concurrent queue, as my collection, omni-blocking collection, we can simplify that. We can have one input queue, one output queue, which we can access unprotected because it's written that way. Threads now work with local data only as before, take their input, produce output, and there are at least two advantages to this over this. Threads can start working immediately, so we can start splitting data, and we just put data into queue, input queue, and when the input queue has any data, threads will kick, and they will start working, they will start work. And we have 3 threads now running at full speed. This one is preparing data, 2 are processing it. Here we had 1 thread followed by 2 threads. Yeah? Now we have do all at the same time, prepare data, process data, which will bring us to the next chapter of my talk. And all this by power of communication and good queue to transfer data around. So this brings us to patterns, which is something which is not really that used at this moment, but I hope will get used more and more. Okay, can I have my... Patterns are prepackaged solutions. I don't really know how to call them. I call them abstractions, I call them building blocks. Now, currently I'm calling them patterns. Let's call them patterns. The idea is that all the complicated stuff, all the multi-threading stuff, everything that will cause you problems, everything that you know a lot before you can write it in the best way is hidden away. You don't have to do it at all. So actually this is a nice implementation of a facade pattern. Take a complicated framework, put a nice facade on it, and say, hey, it's simple. So you can stop caring about how you will do it, and you focus about actually on your problem. So you don't work on plumbing, you work on your application code, of course. And because they offer nice separation between threads with these communication channels usually, most of the time you don't have to care about shared data. Sometimes you do, as you'll see, which makes your code, again, testable. You can test your one data processing block and say, oh, it works. And you depend on the library that it's well tested, that it doesn't have bugs. Well, they all do, but the trick here is if 10,000 people are using this library, they're all testing the same multi-threading kernel. They don't test each their own implementation. So bugs are found faster and they are fixed sooner. If you did everything, you have to repeat your own bugs, which you are only one tester, not 10,000 testers. So in Delphi, we have parallel programming library, which Marco had mentioned. We have my OmniThread library. This one has advantage that it works on all platforms with VCL, FMX, and so on, and console applications and services. This one works only on Windows with VCL applications, console applications, and services. but it's a bit quite more rich, offers more functionality. And just to give you an idea what I'm trying to say here, because it's a concept that's hard to present. I have selected 4 patterns, and I will just scroll to them, just show how they are used. So async await is something that you can easily implement over parallel programming library task, or over a T-thread, or over a normal thread. It's so simple. It says execute a thread, execute a code in some thread, and I don't care about it. And if you implement this as a nice pattern, you just say async, do this. I don't care about tasks, I don't care about threads, I just want this executed. And optionally, you can implement return channels, so when your code is finished, some message goes back to the main thread. Again, you don't care about the mechanism, because that's not your job. You just say await when this ends, and execute this in the main thread, because you should never update user interface in the background thread. And that said, you can create tthread.create anonymous thread is an example of such pattern. You can just add tthread.queue at the end of your code to do the return channel. Or Lazarus has multi-thread procs, when you can use do parallel to execute a procedure in a background thread. This is actually quite more powerful than this, but it also implements async pattern. Next was the future, which I'll just run through because Mark already explained it. Just do the calculation and then at some time access the result. And if the result is not yet ready, the code here will block and wait for the result. Otherwise, it is ready, just pick it up. And again, code is very simple. I say create a future and run this function. I don't care about how this is started. And at some time, I will just read the value and clear the calculation object. My job is done. So that's how the parallel programming should look, not tthread.create, blah, blah, blah. Parallel for, again, takes a range, takes some code, splits this over the range. Each thread works on some subrange. It's very simple to implement. So we usually say parallel, we have almost the same example here. And it's very dangerous. Because what you have now in code, and I don't know how we have the same example, Marco, but we do. This is typical single-threaded code. And it's incredibly simple to convert to parallel version. Just change for to tparallel.for, remove that I becomes, and write this procedure begin and end around. But this is now wrong. It was simple, but it is wrong, because now all my threads are modifying this shared data, which is get. So I have to do the interlocked increment or some variation of that. Powerful, but it will get you into problems because it's so simple. Then I have one from my OmniThread library. Background worker is basically a background server. It gives you input queue, output queue, and you say on how many parallel threads you want to run your server, and then you just throw data at it. Example, you say run this on in two tasks, so on 2 threads. When you get new item to process, do this, and when this result comes back to the main thread, in main thread do this. I don't care how this data goes through the queues to the workers and how it comes back. I just write the code which processes data in a background thread, and I write code which displays the result in my main thread, and I'm done. And somewhere in the code, I have f background worker dot schedule and data packet, which I send in for processing. Okay. And for the last one, I have pipeline with a bit longer story because that's not that trivial to explain. But we have two kinds of processes that are easy to parallelize. One are those that we can throw into parallel for. So if we have data items which do not depend one on each other, we can throw them on data 4 and parallel 4, and parallel 4 we just process this index, this index, this index, this index. Each index is independent. We can fetch it, process it. We may run into problems, but that's always so. And the other is pipeline processes, where we have some data, and when we do some manipulation on that data, and we do some manipulation on the result, and more and more and more. I have something like here, a process which reads data from disk, compresses, let's say it reads a file, compresses the data, encrypts the data, and writes it back to a new folder, for example, and it does this over some big data set, over multiple, many, many, many files. So we can write it like 4 processes, a reader, a compressor, encryptor, and writer. Each of them just says, okay, while I have something to do, I will do what I have to do, read, compress, encrypt, or write. Or we can rewrite them vertical way, not horizontal way. We say, while we have some data to do, while we have files to process, I'll read from this data, compress data, encrypt data, and write data. That's how you would write a single-threaded code. Yeah? Okay, let's complicate this. So this is a pipeline. Data goes through 4 stages, which are independent one on each other, except on the data. They're only dependent on the data that's flowing through. So I can say, okay, I will complicate this. I will say read data into buffer, and then compress this buffer into new buffer, and then encrypt the new buffer into third buffer, and write this buffer out. I'm doing more work to solve the same problem. And now I'll do even more work. I will add communication queues. So while I have data, I will read data, insert it into queue. And then I will read this data back from the queue, compress data, insert it into the next queue. Maybe you all see where I'm going with this. Now I have 4 completely independent parts. This one is reading data from disk and inserting it into queue. Queues are safe. That's what we said before. The second one is reading from a queue, compressing, writing into second queue. It can compress using local data only. So now I can say, okay, these are now my 4 threads. I have complicated and complicated and complicated stuff, but I can use it now in 4 threads. And those 4 threads can overlap each other. The reader has to start first, but then when the reader is reading the second file, the compressor will already begin to work. And when the compressor finishes the first file and starts in the second file, the encryptor can do its work. Another thing that can be written nicely this way is web processing. You have page downloader, you have HTML parser, then you have some indexer or data processor, and you update the database at the end, for example. You can have 2 stages, you can have as many stages as you want. And with OmniThread, okay, now first the diagram. So that's what I did. I have some input, which is, for example, name of my start folder and name of my target folder. I send them into the pipeline. I have the reader here. Reader sends data packets forward. Each packet is 1 file. I have a compressor, which reads from here, sends in output compressed file. Each packet is 1 compressed file, and so on. And I can have the return channel to get some output if I want. The point here is that I only have to write this to get everything to work. Because again, this is a pattern, it's facade. It puts very, very nice front end on a very, very complicated system, and everything else is hidden. Those 4 stages, I will show them in the workshop. Each of them basically does, while I have data, do processing, push data into the next stage. Typical single-threaded code, which is very, very easy to test. Okay, so before I leave you, now your heads are full and will explode anyway. I will leave you with a few things to remember. So if you do locking, always access data in tight, well-tested code. Don't lock for some indefinite amount of time and do all tons of work there. Much better, use well-tested libraries. Use parallel programming library, use tasks, use futures, use parallel4, or use Omnitrail library, or on Lazarus, use multi-thread procs. That's always better than writing your parallel programming framework from scratch. Except if you want to write something better than Borland or I had done, then yes, sure, do it. We'll be happy, I think, to get something better. And when in doubt, we write single-threaded code. Really, the best code is single-threaded code. It's testable, it will work more or less, but you can find bugs in it. In multi-threaded code, you will find bugs after, I don't know, years. I think my record is 1.5 years. For the time that we knew that we have a bug, and before we found it, because it was simply, there was even no shared data. One thread said, destroy the object, use this object somewhere else. It was already destroyed. In single-threaded code, this typically works because memory is still there. You pass this object into some another function, it maybe reads something from this object, maybe writes something to this object. It will work. Yeah, in our case, another thread grabbed this memory block before it was pushed to the next function, and then we had 2 threads working on the same data at random, because this process had 20, 30 different threads. You never know which one will pick this memory block, what we'll do with it, and everything locked from time to time. Only at one customer, only every 3 weeks. Now you find it. So I will leave you with the words from Danny Thorpe, who gave us the name Delphi. He said, new programmers are drawn to multi-threading like moths to flame, with similar results. Okay, keep this in mind. And thank you.